That's cool. I think it's
It's go time.
Well, Pete doesn't need any introduction, but I asked Ruby to get some information to me this morning. So, Pete Sias, N0OY, he's forgotten more about ham radio than any of us will ever know. But, of course, Pete lives west of Salina, and he does a lot of neat things, and we've seen some of his equipment. So, amazing guy. Retired entrepreneur, business owner, specialized in microprocessor design for consumer products and industrial controls. He attended Kansas Technical Institute in Kansas State, studying engineering. Currently serves as an advisor to physics students at Kansas Wesleyan University in Salina. And of course, his hobbies revolve around ham radio and scientific experimentation. First licensed in 1961. That's like a year old.
I was too.
Okay, Pete, it's all yours. Thanks for coming.
Wait a minute, I've forgotten a lot of ham radio too. First license in 68.
Obviously, you figured out my age. So I was in sixth grade in 1961. So that's started my ham radio career. Tonight, I got some slides here. We're going to talk about the Artemis project. I hope this presentation you'll find it entertaining, but it's about a group of us from the Salina area, civilian, non-governmental, not associated with NASA, decided to get together and try to see if we can participate in this NASA project. NASA reached out via a request for information on is there anybody interested in tracking the Artemis spacecraft as it goes to the moon and around and back. And so they sent out a request for information. So, as we know, the Artemis mission is several flights we have coming up. Number 2 just happened on April 1st. And it was a successful flight out and about and around the moon and back. And so it's the second in a series of steps. Now, the third one is going to be land on the moon. And exciting times in the next year or two to establish a moon base for maybe jump off to going to Mars. Who knows how it's going to work. But it's ongoing, and so far, looks like it's going to happen. But NASA had a question to start out. Obviously, they had a lot of questions, but they had a question. They wanted to know who outside NASA could accurately measure spacecraft Doppler. And we all know what Doppler is. It's when an object is coming towards you, is emitting a wave or a sound, it's compressed, the pitch goes up, and it goes away, the pitch goes down. That's the Doppler effect on that. And if you go up in frequency and also speed, then the Doppler spread is much wider. So, for an example, like Coach Keltner here, speeding down I-70, and he is caught on radar and is going to be issued a speeding ticket. I would suggest doing that to help him out is to ask the officer what the Doppler spread in hertz was, and he would do his own calculations in miles per hour. Very simple math, and try to help him either get out of the ticket or get something added on. That's a practical use for Doppler on that. But why does NASA want to do it? Well, NASA uses Doppler to help them keep track of that spacecraft's orientation and trajectory and mile per hour. And by doing it accurately, we can get down into where we can measure like 3 centimeters per second accuracy on does that. I'm still learning how to stick. So I think they went fishing. They sent out an RFI that was available on the internet, a link to it, request for information. Academic, commercial, amateur radio world, anybody can fill that out. I looked at it and I thought it was a very complex problem to tackle just by myself. And so I decided that I don't take the bait. I'm not going to do it. Because tracking the spacecraft at S-band frequencies and measuring the Doppler accurately is something I haven't done and really knew very little about at that time. In the old days, if you wanted to do it as a ham radio operator, you could take and zero beat that signal on your radio and read it out and say, oh, the signal is 1,000.01 megahertz. And then you knew that if you knew that the transmitting frequency was at 1296, 196.0000, then you knew you had 1,000 hertz of Doppler. Pretty crude, pretty rough, but it'll get you in the ballpark. So you can do a back of the envelope calculation with that number of 1,000 hertz, and you can figure out how fast that object that was emitting that signal is going in miles per hour. And so it's, something we can do. NASA wanted us to have sub-hertz accuracy. So we don't have radios that can do that. Now I'll explain how we tackle that problem later. So I kind of thought about this, and I explained to some of the guys back home that it's like NASA comes to us and said, hey, I want you to build a car. Okay. But the only thing we knew about a car was we saw it drive down the street one time. We didn't know there was an engine in it. We didn't know the transmission, gears, or any ratio. So we were really starting from ground zero, blank. But I explained this to people that were interested. Hey, are you going to do this? Are you going to do this? And I kept saying, no, I'm not. A friend of mine called from the Fort Worth area. He works with some of the companies that supply hardware to other government agencies. And he said, we ought to do this. And I gave him the reasons why I didn't think we should do it. But then he said, I've got access to a real powerful computer. It's on loan. And that would really help us do the calculations. So you can write off the problem of not having enough computing power. So that switched my no to yes with the promise of shiny things. And that has happened throughout my life. I'll be starting on a project, I'll be working towards that goal. Out of the periphery, I see something shiny, I turn. And this is what happened there. But I needed help. I had to find some team members. So we'll go through the questions that NASA was interested in. And this is what I had to fill out the night before the deadline. And we submitted it within hours of the deadline. I had no idea how many people were doing it. It was available to anybody, any place in the world. They wanted to know how big a dish size. But they put a cutoff on it and said, we really like you to have at least a 9-meter dish. Mine's 8.5. Close enough to 9 meters. So I had a 28-foot dish. I could check that box. And, okay, we can do that. They wanted to know what was my receiver system. I don't have a receiver system for what frequency they wanted, but I knew how to design one, and I knew how to put one together. But so I had to fill in the blanks as if I was doing the design one. Then they gave us a frequency, and they were very tight about that. They didn't want to give us the frequency of that spacecraft because they were worried about somebody transmitting on that frequency jam. Anyway, the transmit frequency was 2216.5. So really in that band. All spacecraft that is orbiting and sending data down, commercial, governmental, transmit in the S band, 2200 to 2300 megahertz. So that's the band we had to play in, and I do not have the equipment to get into that band, so everything had to be built. They wanted to know about my tracking capability. Well, I can track the moon. That's no problem. I do it with the EME. I can track the sun, other terrestrial bodies for radio astronomy. And I felt I could be accurate enough at that frequency. So I checked that box, yes, and described what we could do. Then they said, are you familiar with I&Q recording? Are you capable of doing Doppler tracking? And they asked about receiver capabilities. Would it have a waterfall, that nice display that you see of the signal? We'll see plenty of them here in a little bit. So I had to answer this question. Yeah, I think I can figure that out. So, and then they wanted to know what type of feed. What kind of feed are you going to put on that dish to illuminate it, to turn it into an effective antenna? And these were a couple of attempts at making feeds for that antenna for that frequency. One is 3D printed, the other one is machined out of aluminum. So that was the RFI, request for information. They wanted to see who could do it. Everybody had to fill this out, send it in, and then, which I did. This was sometime in early December, I believe. Didn't hear anything until a little bit after January. So we set up the hill and waited. And here come the moon, and we waited. By the way, thanks to Tanner for the nice moon shot there. So you can see the 28-foot dish there, and just waiting for an opportunity to play with this. And then we found out we were one of 34 entities selected worldwide to participate. So now it's crunch time. Here we signed up, said we could do it. We're competing against colleges like Stanford and a few other back east Ivy League colleges. A couple ham groups are involved, but the bulk of them were in Europe. Only 14 stations or entities were in the U.S., but most of them were in Europe. So I had to get together and find a team. So I asked around, you want to help me convert this dish to S-band? I'm not on that frequency. We need to get it set up. And surprisingly, I found willing volunteers with very little coercion. I wanted to fine-tune the automatic tracking. I want to be able to set the tracking up and forget about it. But the tracking is different than what we've done before. If you're familiar with low Earth orbit satellite, we use a two-line element database for figuring out the orbit. This spacecraft was heading out into space and was going to intercept the moon. So the tracking information we needed was where is it in space at this particular time as it keeps going out and back. So that required us to write some code. Then we had to decide on what type of SDR receiver, a software-defined receiver. Regular ham radio receiver, you got the knob, you turn the dial, and you talk to people, will not work for this situation. We need something that we could accurate and get the good data, and I'll refer back to that I&Q that was mentioned earlier in the RFI. And then for a wild guess, we figured we needed over 10 terabytes of storage. If we were going to lock onto a carrier and store the data not with the accuracy they wanted. That is a lot of thumb drives, you know. And it's something that, you know, is not practical at all. Okay. Next, tracking code. We needed to give the Artemis data for Artemis as it travels out into space. JPL, NASA, has that. So we wrote a script to go out to their website, grab that data, bring it in, crunch it, so we got an azimuth and an elevation readout for the hill, and plugged it into our tracking system, and then it would point the dish automatically. We did that every 15 seconds. And so we would stay on station. That was one thing that really worked well. We had no trouble with it. And then we had to write the collection code. And it was best done in Unix, or not Unix, but Linux. And Ubuntu was the language of choice that we used at that time. I'll get into the weeds a little bit about that later on how that worked. But we had to write all this code from scratch. We had no patterns. We had really nobody we could talk to. The one person we did reach out to said, "You're starting kind of late, aren't you?" And that's all the help we got. And so, here we are. And looking back at it, I felt like we were like the Little Rascals. You know, that 1930s TV show, Alfalfa, Spanky, you know, Darla, and I felt that's what we were like. We were trying to enter into some big competition against the rich kids, and all we had was a couple of orange crates, some wheels, and maybe some ducks for propulsion. I felt we were really outclassed. We had no idea where we stood in the pecking order or the food chain. But we pressed on. Then we realized our tracking window for Artemis was from around midnight to 8, 9 a.m. That's when it came into view for us in central Kansas. And so it came up in the southeastern sky, October, set in the southwest sky. That's where we could see Artemis. So somebody had to stay up and just babysit the system. Launch day, as part of the crew, we were basically making sure that the rocket got up into orbit and everything was fine. And some of these people were contributors, software, hardware, wiring. For example, we needed real accurate computer clock timing. And most NTP type servers give you a millisecond or so accuracy. We felt we needed sub-nanosecond accuracy. So we had to be down in billions of a second for accuracy on a computer. In hindsight, it's overkill, but we were able to build the equipment to set the timing on all the computers to that sub-billion second accuracy. One of the things we had to do. And there's the basically the workstation that we had to build. Over in this area here was the tracking. Those computers over there interface with the internet. They write it down, crunch the numbers, put it on the screen. We set it to a hardware controller, and that controls the high voltage motors up in the mount that moves the dish and azimuth and elevation. Took care of itself, worked fine. Next station here is the shiny thing. It's sitting there doing a screensaver, but it was central to what we were doing. I'll get into that a little bit more. And then we had this right here. That was our window into the system. As I'll point out later, we had 2 receivers, and we split the energy coming off the dish into a Y. And one of them went to where we could watch, that signal, and we could manipulate it, we could check it, and so it was kind of like a sight glass into an industrial process. We could actually what was going on with that signal. All the time, the other receiver was taking the data, crunching it, and sending it down to the super duper computer right there. By the way, this computer had 1,000 terabytes of storage, and its RAM that we used for cache was 1 terabyte. And so, and then it ran on Linux, and it had 3 blades in it. We'll get into it later, but it was a machine. And how the little rascals got that. Over here was more probably software tweaking area, stuff like this. This was hooked into NASA, watching their live feed, so we could get data off of them that we knew, okay, NASA says they're traveling 5,280 miles an hour. You know, does our back of the envelope calculation jive with that? And we usually get within a couple percent, and which is not bad for just turning dials and reading it off of a screen. So that's kind of the setup. First day I went up there and knew they took lunch at night. I looked up at the dish and I saw these 2 guys up there. I did not know if they were buzzards of doom or if they were buzzards of happiness and success. But anyway, they had parked their feather-laden body up there, and that's how we started out. So let's talk about how we set this all up. We'll run through this dish. 10 for 2.216.5 gigahertz. We come down and go on an amplifier, and we split. And then we jump into 2 different SDR receivers, and then we get a server where we're storing the data, and then we're looking at the live signal tracking and monitoring. These 2 units here were disciplined off of the GPS system, so that was holding them on to a known frequency with fairly good accuracy. I can't give you the parts per million, but it's better than out of the box by using a GPS DO, discipline oscillator, to get us that. And then we come down here, we got, finding updates with JPL, some workstations, and then we got another server down here doing live signal tracking and monitoring. So this is our setup, the one-line diagram, if you will. So to get that dish to work on 2,200 megahertz that I haven't got on before, we needed a way to eliminate that 28-foot dish. And so we started out with something simple by making a helix antenna. And this coil is the actual antenna. We adjust the length, we adjust the diameter, we adjust the pitch, trying to get perfect illumination of a parabolic shape. And when we get perfect illumination, or the best we can, then we have good efficiency. We were striving for. We tried that. We tried this, which happens to be this one right here. It's a very popular design. You notice all the screws on the side. Well, there's a reason for the screws. We need a signal that is circular polarized. We need a signal that goes either right hand or left hand. The spacecraft is transmitting a signal that is right handed. If we don't follow that circular pattern that it's sending that signal down on, and we're saying we're vertical, horizontal, or maybe left, then in a very technical term we say we're cross-threaded. And the signal drops off tremendously. So we had to be on the right hand circular polarization to match that Artemis spacecraft. These screws along the side here, by adjusting those, we affect the weight inside the cavity and get it to rotate that direction. So So that's how we achieve circular rotation using the waveguide cabinet. Moving on, we even tried 3D printing with a different type of horn to spread the signal. We were trying to get maximum illumination without spilling over the edges. What we found, that 6-turn helix, except for left-hand circular polarization, was the win. The way we accomplished this was we would try these feeds. We would go up there on a scaffold and adjust those feeds while a person in a car was a half mile down the road with a signal generator. And we were trying to get max signal by adjusting in and out and focusing these feeds. We were mainly in and out, up and down, and getting it locked in. And then recording that. Then we would come back down off the front of the dish, off the scaffolding, and then command the dish to go point at the sun, and we'd use the sun as a signal generator, and we would compare, did we improve, we were the same, where we were at. We did this, I don't know how many times I climbed that scaffolding up and down, but we eventually decided that the 6-turn helix was going to give us enough signal if everything else worked. So that took a bulk part of the deal. The interesting thing is that NASA decided and would have launched in February. I wouldn't be talking to you today about this. We were not ready in February. We got to go ahead in early January. That gave us about 30 days. If we didn't do all this stuff in 30 days in the winter, no way. We couldn't do it. So when they had a hydrogen link, yeah, we're sorry, but you're gonna give us a window that we can work with. And so April 1st was the limiting date that we could target for. We probably got completed within a day or two before that. We felt comfortable we could go by. Okay, so now we start seeing the I-10, as I call it. How do we test everything? Artemis spacecraft wasn't going to launch until the 1st of April. We wanted to know, do we have enough signal? Does our tracking system work? Can we lock onto a carrier when we don't have any of that stuff other than a signal generator that is a piece of test equipment? We needed real world live type signals. Lo and behold, Korea happened to have an orbiter going around the moon. They put it up about 3 years ago. It's still working. And every hour when that orbiter goes around the moon, there's its signal. Extremely strong. And right here are 2 subbands that are processing the data down. But anyway, there's the carrier. And what that told us, we had about 28 dB of signal-to-noise ratio. Very, very, very strong signal. So the fear of not having enough signal, at least with the Korean orbiter, was put to rest. We now have to hope that the Artemis spacecraft had suitable transmit power. But anyway, this is how we tested. This is on the viewing of the extra SDR receiver. There we're testing the tracking system. There's the actual readout of what the dish is positioned at. Down in the corner you can see our signal generator that we could mimic the S-band signal. We choose 2 of these. normal ham radio stuff up to a few years ago. Turned it on, it had one mixer, it produced a intermediate frequency, but everything that came in had to be probably pre-selected because you had problems coming out of the mixer. I won't get into the detail, but along comes fast enough hardware, analog to digital computer chip, that we could actually take the signal and A to D it right there and turn it into digital data. Then we run it into a mixer, and then we run it into a second mixer. So here's the difference. We shift that second measure to that second mixer 90 degrees. Now we have in phase and quad shift, 90 degrees apart. That's important. So now we're sending to your computer through the USB. We're sending you a stream of values associated with Q and 1. All you're getting is a stream of ones and zeros coming out of it. And what this signal was right here, through here, turned into digital ones and zeros. Your PC over here can reassemble that into the original system. And so that's what we had to do. Here's what your typical stuff looks like in the amateur world: CW, AM, FM, PM, phase modulation. And so then we've got a new term called the phasor diagram. Real quick, I'm spending a lot of time on this, but we have an amplitude vector and we have a phase angle. Okay, the Q represents the amplitude and the phase. So you can see if we were perfect with 90 degrees on each, then we would be right where it's at now. But if we would shift the phase, we could move that pointer over there. Or at this pointer there, depending on our modulation scheme, could be a certain binary value. Real quick, a lot of you guys use PSK, QPSK, quadrature phase shift key. It's 4 bits. So let's say right here, it's bit 0, 0. Over here would be 0, 1, 1, 0, 1, 1. And so when it takes the IQ data and puts it back together, that's how it gives the information into your software that says the guy on the other end just typed an A or a Z or something like that. So that's the new way of handling the data. It'll say things like QAM 256, QAM 2024. You use it every day. Every one of you uses QAM in your system through this, represented through this diagram. And that is when you pick up your phone and you call somebody. All your data is digital, and it goes out through the system. There's I and Q, ones and zeros, put all together. And that's why they can pack so much information in a small bandwidth and cover so many people. So this is the stuff we're using when we pick up our phone. Okay, so the shiny. Let's talk about the shiny thing real quick. Hewlett Packard Edgeline EL8000. Okay. Basically, without saying too much, there's probably a submarine missing a computer. This has so much power in it. When it starts up, the fans sound like your jet engine just before takeoff on a runway. And then they calm down after it reads all the temperatures. So this was a shiny thing that swung my nose into the air. We've got computing power with 1,000 terabytes of storage, and with 1,000 terabytes of storage, and a terabyte of RAM to work with and write our own code. That's how it was configured. You know, it was a loaner, so it had to go back. But while I was there, we put it to the the signal, this is proof. There's the carrier off of that Korean satellite going around the moon. We took the IQ data, went back through, wrote our own software, and we were able to extract the carrier data. And this is the filter range right here. So there was the carrier. That was kind of a sanity check. It was a proof that things were working. Then this is what we were after for. This was showtime. This is the Artemis 6. It's zoomed in on our viewing screen. This light was a little wide, but that is a very, very strong signal for the spacecraft headed towards the moon. There it is normal form. So in order for us to get Doppler, we locked onto this carrier here, and our receiver constantly monitored that frequency, and as it shifted, it would change the IQ value that it was shoving into the super submarine computer. Then every now and then, something would come in and fly into our beam pattern, and there was another satellite or something right there. There's Artemis. There's something else. This maybe lasted 30 seconds. So some type of satellite just happened to be in the right elevation, looking at our beam pattern. So there's activity going on all the time up there. And then one night, this bad boy came in view. This was a really strong signal and wide, dumping a lot of data, so much that it covered up one of the subbands off of the Korean orbit. Lasted 10 seconds. We saw it one other time. It lasted maybe 10 seconds also. Something flew in front of us. It was like we were looking out of a tube towards Artemis, and then something flew in front of us. And then there's other signals that showed up. This one happens to say that we're at 4 degrees elevation, so the dish is very low the ground. Now, if you took that same signal and you zoomed in when NASA said we're sending data, this is what the data looks like at 6 million bits per second. And this is what it looks like in normal time through a normal filter, and that's the one I put on Facebook. So NASA said, hey, we're going to switch to data mode on the carrier, and this is what their data looks like coming down. We have no way to decode it or understand it, but there is a strong signal right there. So, the proof. We took some of the data, we cycled it off after we were done, after they splashed down. And we ran it through our software. And we were looking at it. The things I wanted to put out or show you here was, yeah, they look right at steps. But if you look over here, this is the Doppler in hertz. 7.586. 7.684. The resolution on there, we're carrying out 3 decimal places to the 1,000th of a hertz. It's not bad for the little rascals, we're getting it. Yeah. This confirmed we had a good signal, that this wasn't a fluke. We were actually receiving a good signal, and it correlated with what we were seeing. Signal noise, and the signal above noise right there. So that was the sanity check. It said, yeah, it's working. So in summary, NASA called after we sent the data and said, hey, it looks pretty good. I'm going to give you a gold star. I did not know what a gold star means. I was happy. I would have been happy if I just got a participation trophy. We really worked our butts off trying to get this thing to work and stuff. We were able to receive the signal. We were able to collect it. We had got some output that looks right, and I was happy. I thought that was pretty cool.
Yeah.
So we found out also through NASA that only 24 out of the 34 groups submitted data. So there was a reduction of about a third non-players. We had a great work experience. We spent a lot of hours together. We're still friends. So here's the magic number that we're calling on Friday. This 0.9984 between measured and predicted Doppler. And predicted Doppler was from NASA. So we were really, really close to that. In scientific terms, we could say that's about a 3 sigma. That those points are going to land in that 99 or 99% area of predictability. And I'm glad I said yes to this. Anyway, any questions? This is what we did. Yes?
Did you have a battery backup or a generator backup if you had a power failure in Kansas?
Yeah, we had a universal power system on battery, and we also, if things really went sideways, we had a diesel generator that could tie in. So, yeah, we had all that power, which we didn't need. And, so, that's good.
You said it was left-hand circular polarization.
Right.
Did that change from the outbound to the coming back to the Earth?
Yeah, the spacecraft transmits on right-hand circular polarization. So it's coming down right hand. But it hits the dish. And when it hits the dish, it flips like a mirror. So we have to be left hand at the feed point of the dish to be in sync with it at the right hand coming down. And once again, that was, I hope it's right, type thing. And with the signal levels, yeah, I'll prove that.
But did it change from the outbound when it was going away to when it was coming back?
No. No, the only Doppler we would see would be on the outbound, we would be seeing negative Doppler shift, and on the inbound, the compression, positive Doppler. So, anyway, so Ruby, my partner, aka Darla, put up with me being up there all hours of the night, the day, come in, sleeping until 1 o'clock in the afternoon, getting back out, going back out there, making sure everything is running. The supercomputer, we had it so we could remote into it and keep track of it in other places. We ended up storing almost 8 terabytes of